Hello, students. We are here to discuss hypothesis testing. This is our first lesson in Module 7. While generally, we will be discussing hypothesis testing this whole module, but in this lesson, I will introduce a lot of the terminology, and we will also discuss the one sample t-test. So last module, we discussed parameter estimation and confidence intervals. And this part, the confidence intervals, well, these quantify the precision of the parameter estimate. Well, hypothesis testing, this frames the statistical inference as making a decision between two opposing claims about a parameter using evidence from a data set. And we typically formulate what's called a null hypothesis, written H0, and an alternative hypothesis, H sub A. And these two will be the two opposing claims. Quite often we think about the null hypothesis as saying nothing is happening. And you can think about the alternative hypothesis as saying something is happening. So this is quite often the way we think about these. Generally, we wish to prove the alternative hypothesis, well, that something is happening. But you notice I have this prove in quotes because this is probability and statistics, and nothing is absolute. Nothing is certain. Now, we will calculate how likely we are to observe a data set assuming this null hypothesis is true. And this calculation is used in our decision-making between these two opposing claims. So before I get into that further, let's discuss the 4 steps of hypothesis testing. First, we have to clearly define this H0 and HA. Okay, that's step number 1. Then we have to collect our data. Once we have done that, step 3, we assess the evidence by performing an appropriate test. And throughout this module, we will learn a number of tests. It just depends on what is H0, what is HA, and what are the assumptions about your data set. Finally, we can draw a conclusion based on the result of the appropriate test. So this part is really important that we get right, drawing the conclusion, because as we will see when we work through the Canvas pages, performing the test, we can do in R. And so understanding the results of the test and making a conclusion, that is where your brain comes into the picture. Making a decision with hypothesis testing. The strength of evidence against the null hypothesis is measured with a p-value, and this p-value describes how surprising our data are when the null hypothesis is true. Typically, we use some cutoff to decide how unlikely or how rare our data must be to conclude we have enough evidence against the null hypothesis. And this cutoff is called the significance level of the test, denoted alpha. Most common is alpha equals 0.05. But this does not have to be the only option. So there's 2 possibilities here. We have a significance level alpha. One possibility is the p-value is less than alpha, this significance level. This says our data is rare or surprising enough when H0 is true. Another way to say that is the data provides evidence against H0. In this case, we reject H0. On the other hand, suppose the p-value is greater than alpha. So in this example where alpha is 0.05, maybe our p-value calculated is 0.42. In this case, the data are not surprising enough when H0 is true. Equivalently, the data do not provide evidence against H0. So in this case, we fail to reject H0. Let's discuss these two cases a little more. When P is less than alpha, we say the results are statistically significant and we reject H0. Logically, this very small p-value provides some evidence for this alternative hypothesis. And as I was mentioning, this is typically what we want to prove. Now, if the p-value is bigger than alpha, we say the results are not statistically significant, and we fail to reject H0. But be careful, logically, a large p-value does not prove the null hypothesis. And you can see, as I mentioned, when I was first introducing hypothesis testing, nothing in statistics is absolute due to randomness. So we have to be a little bit careful in our conclusions and the way we phrase things. So when we perform a hypothesis test, there are 4 possible outcomes. Either the null hypothesis is true or false. This is, say, the reality. And then, based on our p-value, we either fail to reject or reject. Okay, so let's discuss these 4 cases. Suppose H0 is true, and we fail to reject H0. This is a true negative. So we have made the right decision. On the other hand, let's go to the other case where we have made the right decision. Suppose H0 is false and we reject. Well, then we have, you can think of this as a true positive. Once again, we have made the right decision. However, the other 2 possibilities, we have made a mistake based on our statistical test. So let's discuss those now. First of all, perhaps the null hypothesis is false, but we have failed to reject it. This you can think of as a false negative. In the language of, say, probability and statistics, we call this a type 2 error. On the other hand, the other mistake, perhaps H0, the null hypothesis is true, and yet we have rejected. So this we can think of as false positive, but in the language of, say, statistics, this is called a type 1 error. The type 1 error and the type 2 error are a result of statistical uncertainty in a hypothesis test. Okay, let's understand the type 1 and type 2 errors through an example. Let's suppose we are testing gene expression. The null hypothesis is that gene G is not expressed in patients with a certain disease, and the alternative hypothesis is that gene G is expressed with patients with a certain disease. A type 1 error, rejection of H0 when it is true. In this example, it would say that we declare gene G relevant to disease D when it is not. So maybe people who have this gene expressed have unnecessary stress, thinking that they might get this disease, or maybe a lot of money is spent trying to create a treatment for the disease based on this type 1 error. Now, the type 1 error rate is the significance level. This alpha is the probability that you reject H0 given it is true. Now, next one, type 2 error. This is a failure to reject H0 when it is false. In this example, it would say that we missed that gene G is relevant to disease D. And perhaps this would prevent us from coming up with the right treatment. So both type 1 error and type 2 errors are not ideal, but they are inherent to a hypothesis test. The type 2 error rate is denoted beta. This is also a probability. And as a note, the probability of detecting a true positive, this would be 1 minus beta, and this is what's called a power of the test. I will just say we will discuss more on power in the next lesson. So this would be lesson 2. So we will discuss power more in the next lesson. Now we're ready to discuss our very first hypothesis test. Now that we have discussed terminology, let's begin. Well, this is hypothesis testing for population mean. So given a population mean mu and a random sample of size n from the normal distribution, mean mu, standard deviation sigma. Suppose our null hypothesis is that mu is some mu 0. Okay, so this is our null hypothesis right here. Well, under the null hypothesis, we know, okay, x bar, so this is the sample mean, minus mu divided by s over the square root of n. This is distributed as a t distribution, n minus 1 degrees of freedom. We discussed this when we discussed sampling distributions. Very nice. So in this case, we have 3 possible alternative hypotheses. One is just that the mean is not equal to mu 0, but then we have these 2 others. Either the mean is bigger than mu 0 or the mean is less than mu 0. So the question becomes, how do we calculate this p-value? Okay, first let's consider the alternative hypothesis where the mean is not equal to mu 0. We have a random sample. We can calculate sample mean, sample standard deviation, and then this t-statistic. The sample mean minus mu 0 divided by s over the square root of n. We will determine how likely it is to see a sample mean at least this far away from mu 0. Or another way to say that is a t-statistic at least this extreme. At least this extreme. Well, the answer to my question, okay, here's the t-distribution. Here is a wonderful t-distribution, probability density function. So let's suppose we have a t-value here. Let's say this is our t observed. Well, the answer, our p-value, will be the probability that t with this n minus 1 degrees of freedom, well, it's at least this far away. So let's draw it here. What this would be all of this. But then also, let's see, all of here. At least this extreme. So I need absolute values here. So the probability that the absolute value is bigger than or equal to the absolute value of my observed. So this is my p-value. It gives us the probability that we see a t-statistic at least as extreme as the one we observed. Now, as a note, we have symmetry of the t probability density function. So this area and this area are the same. So we could write this in terms of a cumulative distribution function, but I'll write it this way, 2 times this area. So my p-value is 2 times the probability that t with n minus 1 degrees of freedom is less than or equal to negative the absolute value of this observed t-statistic. This is really thinking about a cumulative distribution function. All right, this method is called a two-sided t-test. Now, as a remark, with significant level alpha, we reject H0, provided the absolute value of our t-statistic is bigger than or equal to t sub 1 minus alpha over 2 with n minus 1 degrees of freedom, where this is the 1 minus alpha over 2 quantile. 1 minus alpha over 2 quantile. And I have an example here. So what that says is over here, we have alpha over 2 area. And over here, we have alpha over 2 area. And in here, we have area 1 minus alpha. So anytime our calculated t-statistic lies in this yellow, well, then if you took the probability that you have a t-statistic at least this large, thinking area here, it would be less than alpha. We would reject the null. Now, pictures like this, especially this one, right? We have area 1 minus alpha. In the middle, area alpha over 2 and alpha over 2. I hope you are thinking confidence intervals here. And really, this is the right way to think. So, confidence intervals and hypothesis testing for population mean. Well, from Module 6, Lesson 3, when finding a 100 times 1 minus alpha confidence interval for mu using a random sample from the normal distribution and sigma unknown, well, what we could do is convert this inequalities x bar minus mu over s over the square root of n, sitting between these two quantiles, into this confidence interval. So here, this is an interval around mu. Very nice. What does this mean for us? Well, let's suppose we are under the null hypothesis and we calculate our t-statistic. X bar minus mu 0 over s over the square root of n. Then the absolute value of our t-statistic, t observed, is bigger than this 1 minus alpha over 2 quantile. What does that mean about this? Well, it means that my t-statistic is bigger than this number, or it is less than this number. Okay, so it means that mu 0 is not in this confidence interval, which is x bar plus t alpha over 2 n minus 1 s over the square root of n, 2x bar plus t sub 1 minus alpha over 2 n minus 1 degrees of freedom times s over the square root of n. Equivalently, or this means, we go back to our discussion of hypothesis testing, rejecting the null, that mu equals mu 0 at level alpha is equivalent to mu 0 is not in the 100 times 1 minus alpha percent confidence interval, which is created using our sample. And we can always, this is a general statement about hypothesis testing, we can always convert a 100 times 1 minus alpha confidence interval into an alpha level hypothesis test. We will do more of that this module. And the confidence interval, for whatever the parameter is, contains all possible parameters for which the null hypothesis is not rejected. So this is a wonderful thing to think about. Maybe I will make this pink. The last thing that I'll mention is the one-sided t-test for a population mean. In this case, we still have this random sample from the normal distribution, mean mu, standard deviation sigma. We have the same null hypothesis. It's that mu equals some mu zero. But in this case, we have these other alternative hypotheses. One possibility is that mu is bigger than mu zero is our alternative hypothesis, and the other is that mu is less than mu zero. If we are under this alternative hypothesis, we use a p-value that the t distribution is bigger than t observed. So in my picture, t observed is maybe here. And we use the following area. And similarly, if we are with this alternative hypothesis that the mean is less than mu zero, well, maybe our t observed is right here. And the p-value, we want the p-value, we want the probability that the t distribution, n-1 degrees of freedom, is less than or equal to this observed value. We can make a statement in each of these cases about when we reject the null. Here, it's when our observed t-statistic is bigger than the 1 minus alpha quantile. Over here, the observed statistic is less than the alpha quantile. And then finally, this discussion at the bottom is about the corresponding confidence intervals. Okay, so if your observed t-statistic is bigger than the 1 minus alpha quantile, in this case, we reject the null. And so we would conclude, in fact, the data suggests the mean is bigger than mu zero. Why would this make sense for a confidence interval? Well, this mu zero is not in this one-sided confidence interval. That would say, well, in this case, it says mu zero is less than this number. So if this number gives us a lower bound on the mean and mu zero is less than that, you see, this is really what our alternative hypothesis is saying. Similarly, if we go over to the confidence interval statement about this other alternative hypothesis, okay, so our observed t-statistic is less than the alpha quantile for the t distribution, n-1 degrees of freedom. This says this mu zero is not in this one-sided confidence interval. Now, this one-sided confidence interval gives us this upper bound on mu. And if mu zero is not in it, it means mu zero is greater than this number. So if mu zero is greater than our upper bound from the confidence interval, we can safely conclude that the mean is less than mu zero. So here I'm just thinking about this translation between rejecting the null with these two one-sided alternative hypotheses and the corresponding one-sided confidence interval. Okay, you notice I have not done any statistics, any calculation of t-values here, because in reality, we can use R to calculate everything. I really want to discuss the big picture of hypothesis testing and terminology and give you some information about the mathematics and statistics behind this one sample t-test. So thank you very much, class.